In today's video lecture, we're going to finish this packet of notes dealing with operational amplifiers. We're going to start by looking at one final canonical op-amp form, and this is the inverting level shifting amplifier. After we do that, we will summarize some of our results that we've seen with these different canonical forms. Then we're going to talk briefly about multi-stage operational amplifier circuits. These are circuits that have more than one op-amp in them. And finally, we'll look at an application using op-amps in open loop mode. Most of these circuits we've looked at so far have been closed loop configurations, but there is one type of circuit that uses the open loop configuration for the op-amp, and that is the comparator circuit. So we'll look at that very briefly. But let's start with the inverting level shifting amplifier. This is basically a variation of the subtracting amplifier that we saw at last lecture. What makes this circuit different, however, is its application, how it's used. So basically, we're going to have one signal. We're going to call it VA of t, and that's going to be a signal that we want to amplify and that we want to shift its DC offset for. The second signal that we have is VB, which is going to be a DC constant, and that is going to be used to give us our DC offset. It's important to note, however, that the DC offset does not equal VB, but it's based upon VB. Let's look at the configuration. So our signal that we want to amplify, VA of t, is connected through a resistor R1 to the inverting terminal of the op-amp. Then we have a feedback resistor R2, like we've had in most of these canonical forms, connecting the inverting input terminal of the op-amp to the output terminal of the op-amp. Finally, we have this DC signal VB connected between ground and the non-inverting terminal of the op-amp. Let's analyze this circuit and see what we get. The first thing we do is we find the voltage V plus, the voltage at the non-inverting terminal, is equal to just this DC signal VB. And then by virtue of the virtual short circuit approximation, we know that V minus is also equal to VB because of the virtual short circuit approximation. So the voltage at this terminal here is going to be VB. Second thing we do is KCL at the V minus node. So we want to add this current plus this current plus this current equal to 0. The current to the left is VB minus VA of t over R1. Current to the right is the current into the inverting terminal of the op-amp. That's going to be 0 amps. The current going up is VB minus V out of t over R2. The sum of those three currents equals 0. If we solve for V out, we get this result. V out of t is equal to negative R2 over R1 times VA of t plus 1 plus R2 over R1 times VB. This is our equation for the inverting level shifting amplifier. Let's analyze this and see what we have. What we see is our input signal, VA of t, is inverted. That's that minus sign. It is amplified by R2 over R1. So similar to a standard inverting amplifier, we get the same thing here. But the other thing we get, though, is this term on the right. The second term here is our DC offset. Notice, as I said here, the VB signal dictates what the DC offset is, but the DC offset does not equal VB. Specifically, it equals VB times 1 plus R2 over R1. In other words, the gain that we have for VA of t does show up also in the DC offset, so the VB needs to be picked accordingly, as we're going to see in an example on the next page. So what exactly does this circuit do? Let's draw a simple example to show. Suppose the input signal is a sinusoid. The output signal then would be an amplified version of the input that's inverted, and it has a DC offset. So the output might look something like this. With the DC offset, looks like it's about there. So we see that it's amplified. In other words, that is bigger than that, it's amplified. It's inverted, so when this is going up, this is going down, etc. But then the third thing that it adds is this DC offset. It allows us to shift the signal up or down. Before we do an example, let's come up with a slight variation that allows us to have a variable DC offset. If you take your op amp here, and instead of connecting VB directly to the non-inverting terminal of the op amp, we take VB and connect it through a resistor, a potentiometer, and another resistor, and connect that to the non-inverting terminal of the op amp. And let's call this resistor Rx, let's call this resistor Ry, and of course our potentiometer resistor Rpot. So the pot is right there. So you know from looking at potentiometers earlier that when you have a configuration like this, it allows you to set the voltage here to any voltage in the range of 0 to VB volts by choosing Rx and Ry appropriately. So by using this type of configuration connecting to the non-inverting terminal of the op amp, it allows us to get a DC offset here that we can vary just by moving the knob on the potentiometer. Let's do a simple example. Suppose we have an input signal Vn of t that we want to amplify by -14 and then add a 5 volt DC offset. The first thing you need to do is pick R1 and R2 to get the amplification. As we saw on the previous page here, the DC offset is a function of R1 and R2 as well, so we need to pick R1 and R2 before we pick VB. So the first step, pick R1 and R2 to get a gain equal to -14. Specifically, we just set the ratio of R2 to R1 equal to 14. So for example, we could use R2 of 14 kiloohms and R1 of 1 kiloohm. It's not unique, but that would certainly work. The second thing you want to do then is pick VB to get the desired DC offset. Specifically, we know that 1 plus R2 over R1 times VB has to equal 5 volts. That comes from the second part of this expression here. Since R2 over R1 is 14, we get that 15 times VB is equal to 5 volts, where VB is 1/3 of a volt. So one possible design here would be this. We put a 1/3 volt battery here. Then we have our 2 resistors connected to the inverting terminal. R2, 14 kiloohms, R1, 1 kiloohm. And then our signal that we're amplifying, VA of t, is connected to the 1 kiloohm resistor. And of course, we're measuring the output voltage between the output terminal of the op amp and ground. As I pointed out before, the DC value you add here, this 1/3 volt, is not the same as the DC offset you want to end up with, and that's because of this additional term here. You have to remember that. The voltage you're applying to the non-inverting terminal is not equal to the DC voltage you're going to end up with, but it is related to it. Let's look at a variation now. Suppose you wanted to achieve this equation above here, but you did not have a 1/3 volt source available. Suppose you only had a 5 volt source available. So here's a variation using a voltage divider where we can achieve the same goal. So suppose that we only have a 5 volt DC source available. What we can do now is take that 5 volt DC source, put it through a voltage divider. Specifically, if we want 1/3 of a volt here, what we want these resistors to be is a ratio of 5 kiloohms and 70 kiloohms, for example. So now the voltage there, V plus, is what? 5 over 5 plus 70 times 5, or 1/3 of a volt. And of course, the rest of the circuit is the same. We have our 14 kiloohm, our 1 kiloohm, and our input signal here. So notice the use of this voltage divider allows us to get the desired voltage at the non-inverting terminal, in this case 1/3 of a volt, even if we didn't have a 1/3 volt source available. And finally, as I mentioned before in the previous page, if we wanted to have an offset here that varied, we could put a potentiometer here. This allows us to get a range of DC offsets. So that concludes the different canonical amplifiers that we're going to look at in this course. Once again, we had an inverting amplifier, we had a non-inverting amplifier, we had an inverting summing amplifier, we had a subtracting amplifier and a difference amplifier, we had a buffer or voltage follower circuit, and finally we had a level shifting amplifier. Let's sort of summarize some of the observations we made with these. So the first question is, what effect would a load resistance between the output terminal and ground have in these configurations? This is an important question because in all of these op-amp circuits, we're going to be driving something. You have an op-amp circuit, you're going to be driving a motor or a speaker or a light bulb or another circuit or something. And so the question is, when you hook something up to the output terminal of the op-amp, what effect does it have on the op-amp circuit configuration? As we saw in all of these, when we write the KCL equation to find the output voltage, we're not doing it at the output terminal. We're doing the equation at the inverting input terminal. So what we see is that the load resistance has no effect on Vout. There's a caveat here. It has no effect on Vout provided that the op-amp circuit is operating in its linear region and provided that the output current is less than the maximum output current that the op-amp can provide. Does this mean that a load resistance has no effect on the circuit? No, it does not mean that at all, because although the load resistance does not affect the output voltage, it does affect the output current, which means it affects the power coming out of the op-amp. But because the load resistance does not affect the voltage, we basically see that all of these canonical op-amp circuits basically avoid the loading effect. And that is one of the biggest features of these different canonical op-amp configurations, is that you can avoid the loading effect. Second general observation is, what is the general effect of increasing the resistance in the feedback path of each of these configurations? So with the exception of the buffer circuit, which has a gain of 1, all these other circuits have this feedback resistor R2 between the output terminal and the inverting input terminal. And what we see in each of these equations is that that shows up in the numerator of the gain. So that what we see is that increasing the feedback resistor, which is always R2, causes an increase in the gain. And this makes sense because by reducing the current flowing back in this feedback loop, we're making the circuit look more and more like an open loop configuration. We're making it harder for the current to go back, and so it's looking more and more like the open loop configuration. So the next observation is, what is the limit on the size of the input signal for the amplifier to work properly in all of these different configurations? Remember, all of these configurations imply that we're in the linear region of the op-amp. We're not hitting saturation. That means that the magnitude of the gain times our input signal has to be less than or equal to the magnitude of the saturation voltage, which of course in turn depends upon the power supply that is driving the op-amp. So it depends on VCC and VEE. Last observation is, what are the limits on the amount of amplification that can be achieved? We saw in the previous bullet point that the gain times the input signal has to be less than the saturation voltage. So for example, if you know that your input signal can be as high as 1 volt, and if the saturation voltage is 15 volts, you're limited to a gain of 15. Anything greater than that, you could reach saturation. But that is not the only thing that limits the amount of gain. Second observation is, remember the output current, which we haven't talked about too much, but we looked at it in a couple examples. The output current always has to be less than or equal to the maximum output current that the op-amp can handle. Once again, it might be somewhere in 20 to 40 milliamp range. I want to remind you that this depends, among other things, on the load resistance. As the load resistance goes down, the current coming out of the op amp goes up, which means we could reach current saturation earlier. So in other words, voltage saturation can affect how much gain we can get in the op amp, and current saturation can affect how much gain we can get in the op amp. Third thing is you can never get more gain than the open loop gain A of the op amp. In fact, your closed loop gain G is always going to be quite a bit less than the open loop gain A. So in any of these configurations, the gain we end up with G is typically going to be much less than the open loop gain. So in other words, if you have an op amp with an open loop gain of 10 to the 5th, you're not going to be able to get a closed loop gain anywhere close to 10 to the 5th. Now that we've covered these different canonical op amp configurations, let's see what happens when we start combining op amps together. And this is called a multi-stage amplifier circuit. We're going to see that it's actually fairly simple to analyze multi-stage amplifier circuits because you can usually break it down into a whole bunch of simpler problems, and that's because first off, if we have ideal op amps, the output resistance is 0 and the input resistance is infinity. So this means that the different stages of the op amp circuits are not going to affect each other at all. And we're going to see this in an example on the next page. Now, in a practical amplifier, that's not necessarily going to be the case. You might see that the op amps have a slight effect on each other. But in the ideal case, at least, the first op amp, when it's connected to a second op amp, they're not going to affect each other because of the input resistance of each of the op amps being very high and the output resistance being very low. So what that means from an analysis point of view is we can analyze each stage separately and just combine everything at the end. And we'll see this with an example on the next page. So if you look at this circuit, it looks more complicated. It has two different op amps in it, one here and another one here. And we're asked to determine the input-output relationship for this multi-stage amplifier. And we're going to assume an ideal op amp. So the first thing we want to do probably is break this down into the different parts of the circuit. So everything to the left of this line here is our practical source. So we have an input signal VA of t with an internal resistance of, let's say, 50 ohms. We recognize the second part of the circuit as being a buffer circuit. So it's a buffer circuit with a gain equal to 1. The whole idea behind this buffer circuit is it's going to separate the practical source from the rest of the circuit so that this 50 ohm resistance is not going to have an effect on anything. Continuing, we see that this next configuration is just an inverting summing amplifier. It takes two signals, one coming from here and one coming from there, and mixes them together, each with a different gain, to give us an output here. Finally, we're saying that we're driving a 1 kilo ohm load, and we're assuming that there's a small line resistance of 1 ohm here. So this is our output. To analyze this, we can basically look at each stage separately and just put everything together. So if you look at the first stage here, because there's no current into the non-inverting terminal of the op amp, that current is 0. The voltage at this point in the circuit is equal to VA. Now we look at the second stage. It's a buffer amplifier. All that it does is it takes that voltage VA and puts it here. Because of the buffer, this 50 ohm resistor does not have an effect. If we did not have this buffer part of the circuit right here, this 50 ohm resistor would have an effect on the output voltage. But because of the buffer, it's isolated, so it does not have an effect. So now let's look at the inverting summing amplifier. What does it tell us? It tells us that the voltage at this point, this output, we'll call this VC, is what? VC is just the voltage at this point, which is VA times minus 10 over 5. So it's going to be minus 2 VA. And it's also going to add to that VB times minus 10 over 10. So VC is just negative 2 VA minus VB, because it's an inverting summing amplifier with a gain of 2 for this part and a gain of 1 for that part, and then of course it's inverting, so you have a minus sign in front of both. Finally, in this last part, we just see a voltage division. V out is equal to 1,000 over 1 plus 1,000 times VC. So what is V out going to be? V out is going to be 1,000 over 1,001 times what? Times Vc, which is negative 2Va minus Vb. So that is our final answer. Whenever you have a multi-op amp circuit, you can basically divide the circuit up into different parts and see what each part does and then put everything together. That also works from a design perspective. So let's do a multi-op amp problem where we're going to design rather than analyze the circuit. So suppose we have 4 different input signals, V1, V2, V3, V4, and we want to combine them, multiplying V1 by -2, V2 by -4, V3 by +5, and V4 by +10. And we want to create the output based upon that. Turns out there are multiple ways you can do this. One way to realize this function is what? What we could do is combine the -2V1 and the -4V2 using an inverting summing amplifier. You can then realize -5V3 -10V4 with another inverting summing amplifier. Finally, we can subtract the second signal from the first using a difference amplifier. So we take the output of the first inverting summing amplifier, and then we subtract from that the output from the second inverting summing amplifier. That turns those minuses into a plus. This is through a difference amplifier, and this gives us this function here. This is not the only way to realize this function, however. There is another way. We know that with inverting summing amplifiers, you can add as many signals as you want, but they're all going to be inverted. So another thing we could do is we could pass both V3 and V4 into an inverting amplifier of gain -1, and then sum up all 4 signals with an inverting summing amplifier. Once you invert both V3 and V4, we sum V1, V2, -V3, and -V4 with an inverting summing amplifier. If you look at this first approach, we need 1 op amp here for this inverting summing amplifier, a second op amp here with the second inverting summing amplifier, and a third op amp with this difference amplifier. If we use the second approach, you would need 1 op amp to get our inverting amplifier with gain -1, a second op amp to invert V4, and then a third op amp to sum all 4 signals together. So in either one of these designs, it would take 3 op amps. It turns out you can actually realize this function with fewer than 3 op amps. In fact, there's a way to do it with 1 op amp, but the design aspect of it is a little complicated. What I'm going to do on the next page is actually realize this variation here and sort of show how it's done. And I should once again point out that these are not unique. There are many different ways we could realize this function. I just sketched out a couple of the ways here. So let's remind ourselves what we want. We want our V out to be -2 times V1 of t minus 4 times V2 of t plus 5 times V3 of t plus 10 times V4 of t. So what we want to do is we want to separately combine these two together and these two together and then subtract one from the other. So let's start with the V3 and V4. So an inverting summing amplifier would look like what? The non-inverting terminal is grounded. The inverting terminal is connected through 2 resistors to V3 and V4. We have V3. We have V4, and then a feedback resistor here. We want V3 to have a gain of 5 and V4 to have a gain of 10. So one option is to put a 100 kilo ohm resistor here, and then a 10 kilo ohm resistor here. This gives us a ratio of 100 to 10 or 10. And then put a 20 kilo ohm resistor here. This gives us a ratio of 100 over 20, which is 5. So the signal here, because it is an inverting summing amplifier, is going to be what? -5 V3 of t minus 10 V4 of t. Then separately, we are now going to combine V1 and V2. Same way. Non-inverting terminal is grounded. Inverting terminal. We're going to have two resistors here. One connecting to V1. One connecting to V2. And then a feedback resistor here. We want V1 to have a gain of -2. So this feedback resistor here has to be twice as big as this resistor there. So 40/20 will work. And we want V2 to have a gain of -4, which means that this resistor here should be 10 kiloohms. So that gives us a signal at this point of what? It is -2 times V1 of t minus 4 times V2 of t. Finally, what we want to do is we want to subtract this signal from this signal, because ultimately we want a plus 5V3 and a plus 10V4. So we're subtracting -5V3 minus 10V4 from -2V1 minus 4V2. We do that with a difference amplifier. So a difference amplifier looks like what? You have four resistors, R3, R4, R1, and R2. Remember, to get a difference amplifier, we want the ratio of R4 to R3 to be the same as the ratio of R2 to R1. In this case, we want a gain of 1 anyway, so let's make all four resistors the same thing. 10 kiloohm, 10 kiloohm, 10 kiloohm, 10 kiloohm. What this circuit does is it takes the signal here and subtracts the signal here. So the final step then is we just connect this point to there and this point to there, and our V out measured with respect to ground is equal to what? -2V1 minus 4V2 minus -5V3 minus 10V4. So we end up with our final equation, -2V1 minus 4V2 plus 5V3 plus 10V4. And we did this with 1, 2, 3 different op amps. This is an inverting summing amplifier. This is an inverting summing amplifier. This is a difference amplifier. Once again, this is absolutely not unique. As I mentioned on the previous page, we could have just inverted V3 by itself and V4 by itself, and then used a single inverting summing amplifier with 4 inputs to sum up V1, V2, -V3, and -V4, each with the gain that they wanted. -2, -4, -5, and -10. And there are other ways to do it as well. But here, once again, this is just one of the ways we could do this. So for the most part with these op-amp circuits, we've been looking at op-amps in closed loop mode. We said that we normally do not want to use op-amps in open loop mode for a variety of reasons, mostly related to the fact that we don't know exactly what the open loop gain A is. Another reason that we don't use op-amp circuits in open loop mode much is because they saturate very, very quickly. Due to the high gain A in open loop mode, the linear region for an open loop op-amp circuit is very narrow. There is one situation, however, where we want to use saturation to our benefit, and that is a comparator circuit. So let's look at how this comparator circuit works. Our input signal is going to be connected to the non-inverting input terminal of the op-amp, and our reference signal is going to be connected to the inverting terminal of the op-amp. You could, if you wanted to, connect a positive feedback resistor. Normally, remember, we connected negative feedback resistors. This is a positive feedback resistor. It's connected back to the non-inverting terminal of the op. This is an optional positive feedback resistor. It really is not needed, however, because using it in open loop mode works just fine. So we're not going to be using this optional positive feedback resistor. I just wanted to mention it. If you think about how this op-amp works, in the linear region, and that's where the difference between the signal and the reference is within plus and minus V linear, the output is going to be some very large number A times the difference between V plus minus V minus. If the difference between the signal and the reference is greater than the linear region, we're basically going to saturate at the positive voltage, And if the signal minus the reference is less than the linear value, it's going to saturate to negative VSAT. And this is shown on the bottom here. So here we're plotting on the x-axis V signal minus V reference, and on the y-axis we're measuring V out. And what we see is the linear region is going to be very narrow. So V linear is there, and this is going to be negative V linear. Remember, in open loop mode, what is V linear? Is just the saturation voltage divided by the open loop gain A. Since the open loop gain A is very large, this V linear is going to be extremely small. And that means that this region here is extremely narrow. Another way to look at it is the slope of this line here is going to be nearly vertical. Let's sort of plot this slightly differently. Rather than plotting V signal minus V reference, let's just plot V signal on the x-axis, and once again we'll plot V out on the y-axis. What happens now, if V signal is slightly larger than the reference signal, so let's say the reference voltage is right there, if V signal is ever so slightly larger than that, this op-amp output is going to be VSAT. Likewise, if V signal is the slightest bit less than V reference, the op-amp output is going to be negative VSAT. Once again, this is nearly vertical. In fact, the slope is so high, the slope is A, that for all intents and purposes, we say that it is vertical. And this really shows the comparator aspect of an op-amp in open loop mode. Once again, if our signal is greater than the reference, the output voltage will be VSAT. If our signal is less than the reference voltage, the output signal would be negative VSAT. So here we are using the fact that this op-amp saturates very, very quickly and has a very narrow linear region. We're using that to our benefit here. Let's do an example. Before we do this example, I need to give a brief overview of how diodes work. In EE210, we will not use diodes much, but we do use them a little bit specifically in these comparator circuits, so it's important that you understand at least the very basics of how diodes work. So let's do that first, and then we'll get to this problem. So diodes are semiconductor devices that basically are one-way streets. They allow current to flow in one direction, but not the other direction. A symbol for a diode is a triangle with a line like that. Diode allows current to flow in the direction of the arrow, and it does not allow current to flow in the other direction. A light-emitting diode has a symbol very similar, except it has a circle around it. The only difference between a diode and a light-emitting diode is a light-emitting diode lights up when the current flows. So a light-emitting diode, or LED, looks like that. Like a regular diode, it lets current flow in this direction, and when it does, it lights up, and it does not allow current to flow in this direction. One other important thing about diodes is you need what's called a turn-on voltage in order to get the current to start flowing. So turn-on voltage is the minimum positive voltage needed to get the current flowing. And we'll call that turn-on voltage V on. So that would be the voltage across there, V on. So what is the V on? Well, for a regular diode, it's typically something slightly less than 1 volt, typically 0.7 volts. For an LED, the turn-on voltage is typically somewhere in 3 to 4 volt range. In our lab, in fact, 3.3 volts is the turn-on voltage. One final comment about diodes is the brightness of the diode depends upon the current flowing through the diode. The more current, the brighter the LED. That also means the quicker it's going to burn out. So let's now analyze this circuit. So the question is, for what value of V in is the LED on? So the first thing we want to do is we have two different voltage divisions here to look at. One there, one there. On the bottom, remember the current into the op-amp is 0. So in both of these cases, the current into the non-inverting and inverting terminals is 0. So basically, this 3K and 6K resistor on the bottom are, in essence, in series. Technically, they're not in series because there is that wire going into the non-inverting terminal of the op-amp, but because that current is zero, for all intents and purposes, they are in series. So the voltage, V plus, is what? It's going to be 6K over 3K plus 6K times V in, or 2/3 V in. If you look back here, this is our V signal. So the voltage here is 2/3 times V in. Now let's look at the other voltage divider. We see that the voltage here is going to be what? 10 over 10 plus 40 times 5 volts. So V minus is equal to 10 over 10 plus 40 times 5 volts, or 1 volt. So the voltage here is 1 volt. And this is our reference. What we know for the output then is this output is either going to be plus Vsat, and let's assume this is powered by plus or minus 15 volts. So 15 volts and minus 15 volts. So this output voltage is going to be plus 15 volts if what? If V plus is greater than V minus, and this voltage is going to be negative 15 volts if V plus is less than V minus. Then let's think about the LED lighting. For the LED to light, this voltage across it has to be 3.5 volts. Obviously, if you have negative 15 volts at the output of the op-amp, it's not going to light. But if you have plus 15 volts at the output of the op-amp, it will light. So the LED lights if V plus is greater than V minus, or if 2/3 V in is greater than 1 volt, or V in greater than 1.5 volts. So the LED lights if this input signal is 1.5 volts. Once that gets 1.5 volts, the voltage at that point is greater than the voltage at that point, which means the voltage here is 15 volts, which allows current to flow, and the LED lights. And if V in is less than 1.5 volts, V plus is going to be less than V minus, that's the situation down here, and we end up getting the voltage at the output of the op-amp is negative 15 volts, which means that that LED cannot light because the current wants to flow up rather than down, and it cannot do that. Final comment in this example is this R limb. As I mentioned right here, the brightness of the diode depends on the current flowing through the diode. So the purpose of R limb is to control the current flowing through the LED when it's on. And specifically, we can select R limb to get whatever current value we want. We know that when the LED is on, you have 15 volts here and you have 3.5 volts here. ILED is what? It's 15 volts minus 3.5 volts, that is our turn-on voltage, divided by R limb. So in other words, the current through the LED is a function of the saturation voltage of the op-amp, it's a function of the turn-on voltage of the diode, and it's a function of the resistor R limb. And then this could be another design equation, is if you want a particular current, let's say 10 milliamps, which is the typical current that you might want flowing in an LED, you can pick R limb to get that. You will see this in your laboratory where you have to design a comparator circuit. We are certainly not done with op-amps in this course. We're done with this op-amp packet for now, but we will continue to revisit op-amps both in the laboratory and in the lecture later on when we introduce capacitors and inductors. We're going to see later on in this course and in future courses that there are many other interesting circuits that you can build using op-amps. For example, low-pass and high-pass filters. A filter basically blocks certain frequencies from going through the circuit. So a low-pass filter allows low frequencies to pass. A high-pass filter allows high-frequency signals to pass. We will look at these later on in this class. Integrator and differentiator circuits we're going to look at later in this class. They basically use op-amps in conjunction with capacitors and inductors to take an input signal and either integrate it or differentiate it using an op-amp. A rectifier you can think of as an absolute value. So if the input looks something like that, a rectifier circuit full wave rectifier circuit does something like that. There's also something called a half-wave rectifier circuit, which basically just keeps the positive aspects of it. So the red is what's called a half-wave rectifier. The green is what's called a full wave rectifier. There's also a peak detector. So a peak detector basically keeps track of what the maximum voltage of the signal is. So let's say the input looks something like that. What a peak detector would do is it would follow the signal until it hits a maximum, and then it just holds on to that until it gets to the new maximum. That is a peak detector. There's also voltage to current converter. It basically takes a voltage signal and creates a current proportional to that. A current to voltage converter does the exact opposite. Anyway, in this course, we will look at low-pass and high-pass filters using op-amps, and we will look at integrator and differentiator circuits using op-amps. We will look at both of these once we introduce the capacitor and the inductor. These other circuits you will look at in EE310, rectifiers, peak detectors, and voltage to current converters and current to voltage converters. These are all EE310 topics. In summary, op-amp circuits are extremely versatile circuits in electronics. There are so many things that you can do with op-amp circuits. We are only touching the tip of the iceberg in this class. You will see in future classes many different applications of the op-amp circuit. Anyway, that is all for now. Have a good day.